So you can see this one is a different system. As you can notice, here I was forcing W1 plus W2 plus W3 to be equal to 1. But the main thing I'm trying to show you here is how I performed the multiplications after defining the vectors. So when you look at U11, you see that it's just summing V1, V2, and V3, and likewise the sum was done on the right side. Then when I do U22, you'll notice again the sum of the squares for V1, V2, and V3. Now you see that you have U22 operation done for W, for X, and for Y, and then you have these inner product terms here between W and X, between W and Y, and between X and Y. Then when you increase the power to U33, again you see the complexity increases, and the complexity for the type of products also increases. So the orthogonality scheme will take these types of products into account in order to control the behavior of the basis vectors, so that some of these can be sent to 0 and the resulting system will be more easily solvable. Yeah, and you can see the U33 operation on W and on X and on Y. So back to the previous cubic polynomial. So when you simplify this vector, for X, you notice because the complex sinusoid sums to 0, this is actually very, very simple. So we have these relationships. So W is orthogonal to Y, W is orthogonal to X, X is orthogonal to Y, and this is the simplified form for X. And you can see the U11 operation for W is 3. It's not 1 as I showed in that previous example. In this system it's 3. For X it's 0. For Y it is 0, which gives the first equation for me to find R1. And then for U22, because of orthogonality, these will disappear, and the sinusoid, the complex sinusoid with the fundamental frequency being at 3. This one will disappear also. The U22 here will disappear. So now you're left with asking whether U22 for x will disappear, but the idea is for it to remain at this stage, because now we have R1, we deleted R3, we want to find R2. So we don't want it to have a 0 coefficient here. So whatever that is, it is here, and then you can solve for R2 if this is not 0. And then you do the same for R3. So I'm also going to set up the case for the 4th order polynomial to be using this same idea, the idea of orthogonalization, and it will involve powers of the complex sinusoid. But in that case, we'll be dividing, instead of 1/3, we will have 1/4 instead. And the orthogonalization will involve, so you have this first one using the squaring of the entries of y. Now we will have to add another one in which we take into account that we want the combination of y squared with x to go to 0, and then we add another term with y in which we want the combination of x squared with y to go to 0 also, just like these combinations here, x with y squared and y with x squared, and so on, w. So we want R4 to not be present until U44 is being computed on the right side. Then that's when we want it to appear, and by then we hopefully should have found R1, R2, and R3, and only have R4 to go and calculate.